Hello, BSc second year, second sem students. I am today discussing about the last topic of your syllabus, that is ethers and epoxides. So before uh, I will continue, I would like to inform you that our college or our department of chemistry is called for presentation of a photo and poster making competition for all BSc students, and the last date was 16, but it is extended till up to Monday. So the students who are interested, they may take part, and the rules are very simple. You take the photograph or poster of a nearby, or whatever you can think in a poster, or whatever the possible photos you can get, and give an slogan for it and send to us in the Google format, which already sent to you. So I again request all the BSc second sem, fourth sem, and sixth sem students to take the active part in this competition and make it more success. Okay. So on the request of some of the student, the date has been extended. Okay. Now with this point, let me move on to the ethers and epoxides. Okay, so already we have completed carboxylic acids, and today I'm discussing the epoxides and ethers. So nomenclature of ethers and their method of preparation, chemical reactions with hydrogen iodide, that too in hot and cold condition, taking symmetric and unsymmetric ethers. Okay. Then crown ethers, definition, examples, and use of crown ethers as a phase transfer catalyst. Then epoxides. So what are epoxides, and how the synthesis of 1,2-epoxy ether and 1,2-epoxy cyclopropane by acid catalyzed ring opening of 1,2-epoxy cyclopropane in aqueous solution, and their certain chemical properties. Okay, so this is the last topic. It doesn't mean that the portion is over. So here I would like to tell you that even after completion of the portion, I will again and again go through the all the topics which I have discussed with certain questions related to the topic, questions related to that topic, that too for 2 marks and 5 marks, and what to be written for a particular questions, and what would be the question type, that we will discuss in the next coming episodes. Okay, so stating this, let me move on to what are ethers. So ethers are a special organic compound, a class of the organic compound having the general formula ROR or ROR dash to distinguish the two alkyl or aryl groups. Okay, R is an alkyl group or aryl group, O is oxygen, and that oxygen is again related to R or R dash. And here R and R dash, already I have told you, they may be alkyl or aryl group. Okay. Ethers can again be classified into two types. If the two R and R dash are the same, R and R dash are the same. For example, CH3O CH3, CH3O CH3. It is called as a simple keto or simple ether, right? If R and R dash are different, for example, one is CH3, another is C2H5, so ethyl methyl ether. It is called a mixed. That is called unsymmetrical. Unsymmetrical means the two alkyl groups are of the different in nature. One is CH3, another is C2H5. Okay, so we can classify them into two types. One is, the first one is simple, or it is also called as symmetrical, and another is unsymmetrical, means the R and R dash are different. Similarly, you can have another example like CH3O C6H5, phenyl methyl ether, phenyl methyl ether. Okay, so it all depends upon the what type of functional group R is attached to oxygen. Okay, then a typical simple example that generally we use is C2H5O C2H5. It is an ether commonly known as a simple ether which is used as an anesthetic agent. Therefore, most of the time the people are advised to keep a distance away from this, otherwise it will produce soothing effect to the body. Well, now in general, again try to give the definition. The organic compound containing COC, that is ROR linkage, is called as an ether, and they are having the aliphatic, having the general formula CnH2n plus 2O, and ethers are represented by formula ROR, AROR, or AROAR. AR means aromatic ring. Okay, so this is a general way of representation of ethers. So all these you have learned in your PUC, but it's my duty to explain it. So example is dimethyl ether, CH3O CH3. Then this propyl ether, that is CH3 twice CHO, CH again CH3 twice O. Okay, so that is called dispropyl ether. And C2H5O C2H5 diphenyl ether, 2 aromatic ring. Okay, so in the first definition I have told you classification, that is the symmetrical ethers and unsymmetrical ethers. Symmetrical ethers are having 2 alkyl or 2 aryl group same, they are called as a symmetrical. If one alkyl another is aryl, or 2 different aryl, they are called as a unsymmetrical ethers. This I have discussed. Okay, now you can see the nomenclature of ethers. The common name for ether is most simplest is, you can see here, CH3OCH3 dimethyl ether, dimethyl ether, diethyl ether. Okay, it's not di, it's a methyl ethyl ether. Okay, benzene ring plus O C2H5, so it is a phenyl methyl ether. In common system, whatever the type of functional group attached to the oxygen, their name is taken and then it is represented. So in the first case, CH3OCH3, 2 methyl groups, it is called as a dimethyl, and oxygen is therefore it is a ether. Then C2H5O it is a diethyl ether, diethyl ether. Then C2H5CH3 ethyl methyl ether, ethyl methyl ether. It is a third example where you will have mixed ether. Okay, so in common system they are named as taking the name of the 2 alkyl groups and adding the word ether. Okay, so this is naming for your simple diethyl or phenyl or whatever the kinds of ethers. Now according to the UPAC system, okay, in UPAC system the ethers are regarded as a hydrocarbon in which the hydrogen atom is replaced by alkoxy group. The largest group is chosen as a parent hydrocarbon. Okay, you can see CH3OCH3 is a dimethyl ether according to the common system. Now what you have to do, just take CH4. Okay, the H of the CH4 is replaced by O, and that O again attached to the CH3. That means CH3O is methoxy group. Okay, so now what is the name? CH3OCH3. So one of the CH3O is called as methoxy, methoxy, and the hydrocarbon group is methane. So this is the way in which one can write the UPAC naming for ethers. Similarly, you can see C2H5O, OC2H5. So C2H5O is ethoxy group. So ethoxy and the hydrocarbon is C2H5 ether. Okay. Then similarly you can have C2H5O, C2H5, there is a ethyl group, and CH3 group attached to the oxygen. So you can write this as methoxyethane, methoxyethane, but not ethoxymethane. Okay, because the largest hydrocarbon name is written at the end. Okay, so CH3O is a methoxy group attached to the longest carbon C2H5, right? So similarly you can have certain examples here: 2-methyl, 3-methyl, 2-methoxy, that is a CH3O, 2-methoxy, and 2-methyl propane. So you can consider the total number of carbon atoms and then write according to whatever the long chain hydrocarbon it is. And in this case, C6H5O, C2H5. So compared to C2H5, C6H5 is the biggest group. Therefore, it can be represented like ethoxybenzene. Ethoxybenzene. So this is the nomenclature of this compound. So in case of a common name, the two alkyl or aryl groups are named with the term ether, but in UPAC system they are named as alkoxy or benzoxy, okay, group attached to the long chain hydrocarbon. Okay, so this is the naming. Then now you can see the structure similar to the carboxylic acid. Here you can see the CO, okay, that is CH3O, CH3O. So whenever you can see in case of carboxylic acid, aldehydes, ketones, oxygen is containing a lone pair of electron. So similarly here also the oxygen present attached to the 2 CH3 group, 2 CH3 group contain lone pair of electron, and it is sp3 hybridized oxygen. You can see oxygen with a lone pair of electron, and it is attached to the CH3 group and CH3 group, right? So the bond angle between carbon to oxygen and carbon is less than 120. It is almost 110. So here the two bulkier group of CH3 makes the molecule to experience certain pressure. Therefore the molecule is bent, molecular geometry is bent, and the tetrahedral carbon oxygen carbon angle is 110, and the carbon to oxygen is a polar bond, right? So this is the sp3 oxygen with bond angle, bond strength, everything is mentioned here. It is actually the carbon, oxygen, carbon, already I have mentioned 111, but it is a 111.7 degree. Okay, it is not exactly as 120 in case of tetrahedral carbon. So this is to be noticed. Okay, in case of ethers, the oxygen is sp3 hybridized with two lone pair of electrons. Okay, these two lone pair of electrons make it act as a nucleophile. Okay, so this is a simple basic idea you have to remember. Then now we directly move on to the preparation of ethers. So there are few methods I have chosen to make you people to understand how the ethers ROR can be prepared. So using alcohols, that is a dehydration of alcohol, ROH is an alcohol. When two molecules of ROH are subjected for heating in presence of concentrated sulfuric acid or phosphoric acid. So what happens? OH of the one molecule and H of the other molecule of alcohol will eliminate the water, and you will see ROR. So this is what we call it as a dehydration. So what is dehydration? Removal of water molecule in a reaction. Okay, so two alcohol molecule when undergo reaction with a few drops of concentrated sulfuric acid, and the reaction system is heated around 120 to 140 degrees centigrade, elimination of water takes place resulting symmetrical ethers. For example, you can see in the example CH3OH, methyl alcohol, two molecules when subjected for heating in presence of an acid. Here elimination of water molecule takes place to form CH3O, CH3, that is your simple methyl ether or methoxymethane. Okay, so this is elimination of water molecule taking, there is a dehydration taking place. Similarly, two molecules of ethyl alcohol undergo hydrolysis in presence of an acid to give C2H5O, C2H5O plus water. So this is ethyl ether. It's around 88% product will be isolated, right? So dehydration of alcohol, just remember, this is a reaction where elimination of water molecule by two different alcohol leading to an ROR. The most popular method is what we call as a Williams ether synthesis. So this is in PUC also you have learnt. So when sodium alkoxide is treated with an alkyl halide, so what is sodium alkoxide? RONA, treated with RX in a dry ether. That is a specific conditions you have to mention. The condition is it must be both or must be dry. Then what happen? The lone pair of electron and oxygen shift to the alkyl group, and there is a formation of an ether ROR plus NEX, sodium halide. So sodium alkoxide plus alkyl halide RX, when treated in dry condition, they yield ether. So this reaction already you have learned it as a Williams ether synthesis. Okay, ROR plus RX eliminate NaX and to form ROR. Similarly, you can take sodium phenoxide C6H5O minus Na plus and treat with an alkyl halide. So the alkyl halide will eliminate it as NaX and you will get C6H5ONa. Okay, so this is another example for your Williams ether synthesis. Okay, Williams ether synthesis can be used for the preparation of tertiary butyl ether as well as that is anisole. Okay, that is methoxybenzene. Okay, so other two examples are there, but at least you remember the above two, that is sufficient, right? Now similarly, the another example is there, diazomethane compound, using diazomethane compound. Okay, now you can see here, when alcohol or OH treated with diazomethane. What is diazomethane? It is CH2 minus N triple bond N and central nitrogen is having plus. It is actually a diazonium chloride, but diazomethane is CH2 minus and N plus triple bond N in presence of what you see, in presence of fluorobromic acid HBF4, and just heat it, you will get ROCH3 and elimination of nitrogen. Okay, elimination of nitrogen takes place and the CH2 group will attack to this oxygen as a CH3. Okay, so this is a diazomethane reaction. So you can take methyl alcohol and treat with a diazomethane compound and you will yield dyes with the dimethyl ether with the elimination of nitrogen. Okay, so similarly phenol you can take and you will get anisole, that is C6H5O CH3. It is called as anisole, or you can write methoxybenzene or phenoxymethane. Okay, so like this the synthesis or preparation of various type of what we say ethers can be done. Then now you can see the properties of these compounds. Okay, so for this you can see ethanol. What is the molecular weight? 46. That is CH3CH2OH. Dimethyl ether CH3O CH3 is also having the same molecular formula, and again is having a propane where C2H5 C2H5 CH3 long chain hydrocarbon. Okay, they are having 46, 46, 43. These are the molecular formula. Now let us see the boiling point of this compound. Okay, so in case of alcohol, the boiling point is nearly 78, and dimethyl ether CH3O CH3, it is having a boiling point of minus 25, and that as the open chain hydrocarbon with the 3 carbons is having minus 42. So on looking this, you can come to a conclusion that the presence of oxygen will reduce the boiling point in case of ether, but the same oxygen which is present in alcohol, it is 78 degrees centigrade. So the lowering of a boiling point is due to the structural difference between the 3 compounds. And if you talk about the solubility, ether are less soluble, okay, less soluble than water, in water than alcohols, because in alcohol there is a formation of hydrogen bonding between OH and O of two different alcohol molecule. But in case of ether, the hydrogen bonding is not possible like alcohol, and they are more water soluble, okay, than that of the alcohol. Then now we move on to, after physical property, move to the chemical properties. So chemical properties of ROR. As per your syllabus, they have mentioned specific properties. Cleavage of ether by hot concentrated acids. Okay, so when ethers are treated with different reagent, what would be the effect? So ethers are quite stable compound, but they react under strong conditions. When ethers are heated in concentrated acid like H2SO4, the ether linkage is broken and the product are different in nature. For example, when you take ROR, a general example, okay, ether when treated with a halogen acid, concentrated halogen acid HX maybe, it may be HCl, it may be HBr, or it may be HI. Okay, best example is HI. When heated, it will go to give ROH and RX, alcohol and alkyl halides are formed. So ethers on heated with the concentrated HX, okay, so there is a formation of alcohol and RX. Now similarly you can see C2 CH3 CH2O CH2 CH3, that is a diethyl ether when treated with HI, concentrated HI, there is a formation of alcohol, ethanol, plus CH3 CH2I, that is ethyl iodide. So what happens actually, the oxygen and C2H5 group, oxygen and C2H5 group will rupture, broken, and it will be get converted into iodine is added to C2H5 group as C2H5I, and the earlier part, that C2H5O will become C2H5OH. So here this reaction occur. The acids most often used in these reactions are HI, HBr and HCl, and it is found that HI is more frequently used rather than HBr and HCl because HI, the iodine, is more electronegative than Br and Cl. That is the reason why we choose for this cleavage or breakage of OR bond by using HI. Okay, so let me see the specific example. When HI is heated, okay, reaction in a hot and cold condition, what would be the product? A simple ether reacts with a concentrated HI, hydrogen iodide, in cold condition to produce alcohol and corresponding alkyl halide. Okay, so you can see. So when your CH3OCH3 and HI treated around 0 degree centigrade at cooled condition, then the compound what you get by the rupture of oxygen CH3 bond broken, and it will give CH3OH. The H of the HI will be added and iodine will be added to the CH3. So you will get CH3 methyl iodide. Okay, so this is a particular reaction which is carried out in cold condition with the HI. Okay, so similarly you can see ethyl methyl ether when heated with HI at 0 degree centigrade, there is a formation of ethanol plus CH3I methyl iodide. So whatever the reaction product is there, it is nothing but preparation of alcohol also. Okay, so in general, in cold condition, when HI hydrogen iodide at 0 degree centigrade treated with diethyl ether, there is a formation of methanol and methyl iodide. Now what happens if the same reaction is used with hot condition? Okay, so let us see. Yes, similarly, when ether is heated with HI in a hot condition, okay, so what would be the reaction? For example, C2H5O C2H5, it is a diethyl ether. When heated, here what happens is elimination of water molecule, that is the oxygen of 2 C2H5 group and the hydrogen of HI will be eliminated as H2O, and there is a formation of C2H5I. C2H5I, that is a ethyl iodide. Okay, so in earlier case there is a formation of alcohol and alkyl halide in cold condition, but in hot condition this is the change, the water molecule elimination and ethyl iodide. So in examination the examiner is very particular to ask you what is the effect of HI with simple ether or dimethyl ether in hot and cold condition. So if that is the question, you have to write both the reaction. In hot condition, C2H5O C2H5 will get converted into ethanol plus methyl iodide in cold condition. In hot condition, there is a 2 molecules of ethyl iodide and water formation. So that is the difference you have to remember, and according to the question you must able to write. Okay, so you can see another example, C2H5O C2H5 CH3. Again you will get a C2H5I and CH3I plus water. Similarly, anisole when treated with HI, there is a formation of phenol and methyl iodide. Okay, so these are the two typical examples you have to remember with respect to action of HI in hot condition as well as in cold condition. Okay, in a cold condition there is a formation of alcohol and alkyl halide. In case of hot condition, 2 molecules of alkyl halide and water formation. Reaction with dilute sulfuric acid. So dimethyl ether or ethyl methyl ether when heated with dilute sulfuric acid, so there is a formation of alcohol, ethyl alcohol C2H5OH. Okay, addition of water takes place and converts the ether into alcohol. Similarly, you can see C2H5O CH3 will get converting into ethyl alcohol and methyl alcohol respectively. Okay, so this is the reaction with respect to dilute sulfuric acid. Okay, now with this we move on to the other aspect of this topic, that is epoxides. So what are epoxide? Epoxides are cyclic compound containing an oxygen, that means the cyclic hydrocarbons, that is CH2 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 and there must be one oxygen. So such cyclic compounds are called as epoxide. For example, I have given R dash, that is a carbon, and another R dash carbon, but oxygen is there in the ring system. So a cyclic compound containing the hydrocarbon with oxygen in the ring system is called as an epoxide. Okay, the three-membered oxarine ring is a parent where oxygen is taken as a number one, and the remaining two carbon are taken as 2 and 3, and the various substituents are named according to their system. Okay, so the best example here I have chosen is, you can see, CH2O CH2. It is a simple oxarine, or it is also called as 1,2-epoxyethane. 1,2-epoxyethane. Similarly, you can see the another example here. 2,5,2,5 diethyl 3 on the third carbon atom. Isopropyl butane, isopropyl oxarine. Okay, and another example, you can see the R and R can be changed by CH3O and CH3 groups, that is trans 2-methoxy 3-methyl oxarine. Okay, so these are some example. Simply, you don't worry about these example. These are a little bit complicated. Only you try to remember this. That is here CH2 CH2O, a simple epoxy compound. Okay, in the next you can see cyclic ethers epoxides. That is, you can see 5-membered ring containing an oxygen. It is called as a CH2 CH2 CH2, 4-membered carbon containing oxygen in between the two ring system. That is called tetrahydrofuran. CH2 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 CH2O. The first compound is the tetrahedron. Now similarly the same compound, but the difference is 2 hydrogen atoms of the carbon 1, 2 and 3, 4 are removed, and it is called simply furan. Okay, CH double bond CH, again CH double bond CHO in the ring system. Okay, it is simple furan. Tetrahydrofuran, CH2 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 4 times, and oxygen in the ring system. And here CH double bond CH, CH double bond CH, oxygen, furan. And the next one is oxarine. Okay, so this is also an example connected to epoxide. Similarly, 6-membered ring type compound containing 2 oxygen. So these two are named or numbered as 1 and 4. 1, 2, 3, 4, 5, 6. So in the 6-membered ring at 1 and 4 there is oxygen. It is called 1,4. Okay, dioxine. Okay, so these are some of the examples connected to your cyclic ethers. Okay, they are also called as epoxides. So epoxides are cyclic ethers in which the ether oxygen is present in the ring system. Okay, the most simplest example that we can give is ethylene epoxide. What is ethylene epoxide? CH2O CH2. Okay, then preparation. So when you take an unsaturated hydrocarbon, for example, here, this one, CH2 double bond CH2, CH2 double bond CH2, ethene. When it is allowed to react with RC double bond OH, 2OO, that is called a peroxy acids. RCOH is an acid, but another oxygen is extra, therefore it is called as a peroxy acids. Okay, so when it is treated with the peroxy acids, then what happens? The one of the oxygen of the OOH group is under cyclic process to form your cyclic oxygen containing compound plus RCOH. Okay, so this is your conversion of unsaturated hydrocarbon into a cyclic epoxide. Okay, so you will get a CH2CH2O. Okay, ethylene epoxide. Similarly, you can see cyclohexene C6 CH2 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 CH2. At the one end there is a double bond, cyclohexene. When treated with metachloropropyl benzoic acid, that is called as a MCPBA. Okay, so it is a reagent. So in presence of this, the reaction is carried out with dichloromethane as a solvent media. What happened? The double bond opens and oxygen is in between the ring system. So you can see the typical structure, that is epoxy cyclohexane. It is called epoxy cyclohexane. So as per your syllabus, they have mentioned the preparation of epoxy compound. So the first one is you can take CH2 double bond CH2 ethene and treat with your RCOOR, that is a organic R acid containing an additional oxygen. It's called a per. So per organic acids. Okay, there is a formation of epoxy compound. Similarly, cyclohexene, when treated with metachloro peroxybenzoic acid. Okay, so you can see what is that metachloroperoxybenzoic acid. C6H5 is a meta position chlorine, and COOH, that is a peroxy acid, peroxy or peroxy acid. So this is a reagent which is used as an intermediate. Okay, so insertion of oxygen leads to the formation of epoxy cyclohexane. Epoxy cyclohexane means a cyclohexane is there and the oxygen is in between the two carbon atoms. So this is a possibility, right? So in generally, the properties of epoxides we have to consider. Epoxides are much more reactive than the simple ethers. The reason is very simple. The CH2 group is under three-membered ring, or under tense, or under pressure, or under strain. Therefore, whenever the nucleophile, electrophile, even water molecule comes to it, it undergo ring opening reaction. Okay, one by one you can see the examples here. Okay, acid catalyzed ring opening of epoxides in water to form diol compound. You can see RCHOCHR. So this is a cyclic compound containing oxygen. It is a generally you can say a epoxide type compound, not ethylene epoxide, alkyl substituted ethylene epoxide. When it is added to water molecule, so carbon to oxygen bond broken, and the O will become OH, and the OH of the water molecule will attach to the another carbon, and you will get 2,3 diol. Okay, diol, dihydroxy alcohol, it's called a diol, will going to form. So here the oxygen to carbon ring rupturing, ring breaking reaction occurs, and H is added to the oxygen, and the remaining OH group attached to the carbon ring of the system. So sudden opening of the ring system can possible with the action of water. Okay, then similarly the acid catalyzed ring opening reaction, you can see a specific example, CH3OH alcohol when treated with RCHOCHR. Okay, so here in presence of an acid, it will going to convert it into, that is a CH3OH. CH3 will attach to the carbon, and the OH is added to the another carbon. Okay, so here I mean to say that CHO, CH, this is a ring system. The CHO, this one side bond is open or broken, okay, and the O will be attacked, the OH group will attack to this carbon, and CH3 will group attached to the oxygen. So you will get RCH, OH, CH, OCH3H. That is a methoxy alcohol, methoxy substituted alcohol, alkoxy group attached here. So it is called alkoxy alcohol or methoxy. You can say OCH3 is a methoxy group. Methoxy long chain alcohol compound will going to form. Okay, so this is a reaction. Similarly, you can see the same type of ring opening reaction when treated with HX, halogen acid. Okay, so when HX is treated, the rupture occurs and the O will converted into OH and X is added to the other carbon. So halogen substituted alcohol will going to form. Halogen substituted alcohol will going to form. Okay, when you treat with the Grignard reagent RMgX, okay, in presence of an acid, so what happened? It may be RMgX or R lithium, alkyl lithium compound. So you will get converting that the R group attached to the first carbon, RCHR dash, okay, and the O will be converted into CHOHR. Okay, so this conversion is possible. So here the rupture of carbon to oxygen occurs, and to that carbon atom R will be added and O will become OH. So alkyl substituted, dialkyl substituted alcohols are formed. That is, simple alcohols are formed when a Grignard reagent RMgX is added. The R of the MgX attack to the carbon and undergo process of hydrolysis to convert the O into alcohol. Now similarly, the ring opening reaction with amines. Okay, for example, methylamine CH3NH2 or CHOOHR. It is your epoxy compound. When treated with amine, what happened to product? You can see that NH2CH3, the NH group attack to the carbon and O will be converted into OH. It is amino alcohol will going to forms, that is called amines. Okay, RCHOH CHNH CH3H. So here actually the CHO bond opens. Okay, CHO bond opens and O will become OH, okay, by CH3NH2, and the remaining is NHCH3 attacked to the another carbon. So you will get amino alcohols. Now the last part of this topic, that is crown ethers. What are crown ethers? It is a new technical word for you people. Okay, crown ethers. Crown is just like a cap on the head of a king. So here a crown is there. So what kind of crown? It is a chemical crown. So you can see crown ethers are containing the epoxy compound, that is a cyclic epoxy compound with large number of carbon and oxygen in its ring system. Okay, so I have given one example to make it clear understanding. I have written it as a 12 crown 4. So what is this 12? 12 is the total number of carbon and oxygen present in the ring system. Now you can count 1 carbon, second carbon, oxygen third, 4, 5, 6, 7, 8, 9, 10, 11, 12. So out of these 12 elements of carbon and oxygen in the ring system, 12 is a ring system where the total number of carbon and oxygen are present. And 4, what is that 4 indicates? the oxygen. Now we can just make a glance. Carbon, oxygen, carbon. So what is this? Ether. Okay. So one ether molecule, two ether molecule, three ether molecule, four ether molecules, they are joined in a cyclic order where total there are 12 carbon and oxygen atoms with 4 oxygen in the ring system. So it is called as 12 crown 4 ether. 12 crown 4 ether. So it is an ether molecule, cyclic ether, right? Okay. Now crown ethers, the word itself indicates ethers in a ring system where the two carbon and oxygens are continuously joined in a ring system. Okay. Now you can see the definition. Crown ethers are named as X crown Y, where X is the total number of atoms in the ring system, carbon and oxygen, and Y is the number of oxygen present in the ring system. For example, 18 crown 6 ether, that is it is 18 member ring and 6 is a oxygen atoms. So in generally you try to understand, that is ROR, that is, or in general I will write CH3O CH3. Okay, so it is your ether. If it is in a cyclic system, it will become CH2O CH2, again CH2O 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 CH2O, so and so forth. So here large number of carbon are in the ring system. So the X is the total number of atoms in the ring system and Y is number of oxygen present in the that particular system. Okay, so you can see here, you can see how many carbon and oxygen are there in the crown ether. So you can count. There are first central oxygen 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18. So totally there are 18 carbon and oxygen in the ring system, but there are 2 cyclohexane rings are there at the ring system at the center. Now what is 6? 6 is a number of oxygen. So in the 18 membered ring system, there are totally 18 atoms, out of which 6 are oxygen. Okay, 6 are oxygen. So the name of this compound is 18 crown 6, or else 2 cyclohexane compounds are there. It is called as dicyclohexane 18 crown 6 ether. Okay, so this is the simple definition you can remember, that OCH2 CH2 OCH2 CH2 OCH2 CH2 OCH2 CH2 OCH2 CH2, n number of carbon and oxygen, they are in the ring system. So large number of carbon oxygen ring system are considered as crown ethers, and overall it looks like a rangoli in our term, but it is not a rangoli, it is a crown. And in the every oxygen atoms which are there in the ring system possess lone pair of electron, and these lone pair of electrons makes the crown ethers to play an important role for the isolation or purification of inorganic minerals. Okay, for example, if sodium is there, sodium is a plus. Okay, and this all the oxygens are minus delta. So what they will do, the minus delta charge present on the oxygen hold the positive metal ion like potassium, magnesium, anything in the center. So the metal is at the center with the metal oxygen bond, and it looks like a crown, okay, with a king at the center. So this is the beauty of these crown ethers. So I will give you in the next slide how it works. Okay, now in generally there are definitions I have given. What are crown ethers and how they are synthesized? Crown ethers are a cyclic compound containing several ether linkage around central cavity, right? Crown ethers specifically binds certain metal atoms or ions in the molecule. The crown ether is called the host. Okay, crown ether is called host, and the species that binds at the center is called as a guest. Crown ethers are named X, crown Y, where X is the total number of atoms, that is carbon and oxygen in the ring system, and Y is the number of oxygen present in the ring system. Okay, binding of Na plus and crown ethers are through interaction of a positively charged ion with a lone pair of electrons present on the oxygen atom. Okay, crown ethers are soluble in non-polar solvent. Okay, now you can see this in example. 15 crown 5. So what is this 15? The total number of elements present in this particular crown ether is 15. You can count the total number of oxygen and carbon in the ring system. What is that? 5. 5 is the 5 oxygens involved in that ring system. Okay, so it is 15 crown 5, and each oxygen containing lone pair of electrons, that is a minus delta charge is there, and this minus delta charge, when allowed to react with a metal like sodium in the mixture, okay, so sodium will be held exactly at the center of the crown ether, and you will get Na with oxygen dotted line bond. You can see here. Okay, so this is a complex type compound will going to form. So Na is the metal Na in the present of a mixture will be extracted by the crown ethers, and there is a Na plus and oxygen, Na plus and oxygen, Na plus and oxygen, that will going to make the important separation of Na plus ion in the mixture. Okay, so this is a good technique to separate most of the cations from their minerals or from their solution state by treating with the crown ethers. Okay, so just you can imagine, not only Na, even you can take the gold which is present in the mineral and treat with crown ethers for several hours, keep it. So it is possible that Au, gold, may come in the ring system where the total number of carbon and oxygen in the ring system is more than 35. Okay, such a huge crown ether first prepared, and it is then allowed to react with the minerals of the gold. The gold coin or the gold ions are settled at the bottom. That is the most important application, and if this whatever I am thinking is true, then definitely one can extract gold from the minerals very easily by treating with ether in a solvent and keep it for several hours or several days. After sometimes the ions may get present exactly at the center of the crown. Okay, now these crown ethers, just you can see, potassium can be separated from KMnO4. Similarly, you can see the purple benzene ring. Okay, benzene type ring, center potassium. Okay, so these are the some of the synthetic applications of crown ethers in the purification of most of the inorganic ions. Okay, so crown ether will look like this. Okay, you can see here in the first case there is a lithium. Okay, in the second case the sodium, 12 crown 4 lithium, and 15 crown 5 sodium, and here 18 crown 6 solvent K plus, that is a K plus. Okay, so here you can see a typical colored structure of 18 crown 6 with K plus solvent. Okay, so you can see the beautiful color. All the carbon hydrogen which are almost it is a white color, and at the center there is a potassium, and that potassium is making the bond with the oxygen. Okay, and it is a hold exactly at the center. So this particular crown ether is used for purification of metallic ions from their solution or from their minerals. Okay, now you can see how exactly it looks. It's a beautiful color combination you can observe. Okay, so all these crown ethers can be complex metal cation in the center of the ring system. The size of the ether ring will determine which cation it can fit or it can react. Okay, then uh, complexation by crown ether often allow polar inorganic salts to dissolve in non-polar organic solvents. Okay, so polar and non-polar you might be observing. So water H2O, H plus, okay, and O minus, it is a polar solvent, and non-polar solvent means benzene organic compound. Okay, so for that also it is a useful. Then utility of crown ether. So where the crown ethers are utilized. Okay, the utility of crown ethers in separating a mixture of cations, that is a high degree selectivity, enable the crown ethers compounds to identify the guest atom in the solution and wrap around it. Crown ethers are widely used in organic synthesis. Okay, crown ethers are useful in phase transfer catalyst. Nowadays, this is a very important, and I will discuss this phase transfer catalyst in the next episode. Okay, so in the phase transfer catalyst, these crown ethers play an important. That means you take the reaction system A and B, add crown ether, and keep it for several hours or several minutes, and shake it, and after that, the phase transfer, that is a in a solvent or a solution where the reactants are placed and crown ethers are added and observed after 2 hours or 3 hours or after 2 days, what happened, the phase solvent phase is get removed and the reactant or final product will be in your crown ether system. So that phase transfer catalytic reaction I will discuss later on. Then crown ethers are most frequently used to complex cations, amines, phenol reactions, etc. So with this, I would like to thank you one and all for your patience hearing. Okay, and with this, at present, I would say my portion is over, but it is not over, because next week onwards, what I will do is I will take one by one topic in slow, not a hard condition, in a slow process, and the important reactions again I will discuss with questions. Okay, and my intention is, let me provide you the study material. Whatever the slides I have shown, they are running slides, but now what I will do is I will take the selected part of the topic, that is the slides, and send to you after my next week discussion. Each week I will going to send the study material in WhatsApp page or WhatsApp group, so you can either note down or else you can make printout of that and take it as a notes, as a work, that is your study material. Okay, so my young students, so still the corona is playing a vital role. It is a very difficult when the school and colleges may open, but according to me, probably in the month of July, your classes may begin or college may reopen, but condition is very difficult because all the students must undergo vaccination, and you bring the vaccination report to the college and then attend the class. That may be the very tough time. So as far as possible, from 21st, I think 21st June onwards, above 18 students are eligible to take the vaccination. So I request all of you, let us take the vaccine, and at least from the next month you do attend the theory and practicals. Okay, so if theory and practicals are open, definitely we will continue offline. Otherwise, online classes will be as it is, and there is a no other go for me and no other way for you also. So, if you have any doubts, any queries, now in your group you put certain questions to me or my colleagues regarding the topic. So, with this, I would like to uh, complete your portion at this stage, and we will meet again next week. Okay, so till that I say goodbye. Thank you.